right, so let's continue with function, and I start talking about it from the beginning. Okay, so a function of f from a to b is an assignment of exactly one element of b to each element of a. I will show you also in detail in one example that how it works. You will understand much better. But let's continue. We write f a equal to b if b is the unique element of b assigned by the function f to the element a of a. So a and b that we define here, they are sets, okay, non-empty sets. We show them by capital letters, and a and b are just elements of them. So in another word, a is the input and b is the output. But there are also some names we correspond to them, and I will tell you about them as well. And also we can call such a case a mapping from this set to the other one. Let me see if there is still a problem or not. Let me check. I think there is a problem with one of you guys, so you should again restart it if you can't hear me, because everyone can hear me now. Okay, so let me continue. Okay, so let's move on. I want to talk about the names that we use for, let me activate laser. Yes. So there are some specific names that we use in functions like domain, codomain, and range of a function, or even image inside a function. So f is a function from a to b. We assume that. Then we say that a is the domain of f. So a as the input set inside the function, we call it domain. And codomain is the set that we are trying to map to. In a picture, I will show you much better what do we mean by that. And if we have one arbitrary element from A, we can say FA is equal to B. Then we call this value the image of A. So this one, and the collection of these images, we call them range of the function. So domain is actually the set inside the function which we show with A capital. And A is just a pre-image of that. So sometimes we have this mistake that A, for example, is a domain. No, A is just an element inside that domain. So we shouldn't make that mistake. In this picture, it's more obvious that's what we are doing. So first of all, we are mapping from the set A to the set B. So as you can see, it was very important to know about sets before knowing about the function. And all the possible values that we can have here is related to the set A, and which is our domain. And B here is our codomain. All the possible values that are available for us inside this set. So you can take an arbitrary number inside this set, call it A, and this is the pre-image of B, which is the image of A. So whenever you insert A inside this function, the output should be B. So in a simple way to say, whenever you use A inside F, you will get as an output B. In examples, it will be more obvious, and I'm sure all of you already seen it in high school and also calculus. So as an example, let's this function to map from integer to another set of integer. So it actually consider the whole integer numbers as the all possibilities. Whether we use all the elements inside integer, then we will talk about the properties related to that. Now, if we define this function as fx, which is our input, is equal to x power 2, The whole thing here will decide about our output. So where the domain of f is the set of all integers. Yeah, here define it. This is our domain, which is all integers. What about the range of it? When we talk about the range of it, range is the collection of the images. So it's not necessarily the codomain that you have here. Not necessarily you will reach all the integers for your range. So what's the range? One by one, starting from the initial point, we can start it. If you consider 0 inside integers, which is, it's not like natural numbers, so you start from 0. So 0 inside this function will give us 0 power 2, which is 0. So 0 is an image of 0, which we write here. Again, the second one, 1 power 2 is 1. 2 power 2 is 4. And we continue. The collection of all of that will make a set. And we call it image, actually we call it range of the function, which each one of them are actually image of one arbitrary number. So we have different types of functions. For example, one-to-one. In this case, FA, whenever we have FA is equal to FB, it should imply that A is equal to B. So whenever you have these two images, it should for sure derive from the same variable. Again, in that example, I will show you much better. Here would be the best time to explain about it. It means that whenever you have, for example, this case, let me also show you in one picture, maybe that would be much better to understand. Like, for example, this case. Now we have a line. First of all, I may ask you whether this line is a function or not. You can consider this one as x-axis and this one as y. Y is actually equal to x. This is the way that you can draw a function, right? So if I want to check whether this is a function or not, what should I do? I should draw parallel lines to my y-axis like this. If it cuts only maximum 1 point from this line, you see only at 1 point, and this is a function. So we should be careful that for each unique x, I should have either 0 or 1 corresponding y. If it has more, it means that this is not a function. For example, if you have a parabola like this, then in that case, if you draw a line which is parallel to y-axis, then you can see it cuts it in 2 points. So this is not a function. So when I talk about one-to-one function, it's a specific function. It means that first of all, we shouldn't have such a case because it should be a function, first of all. And next, we should check whether if I draw parallel lines to my x-axis, it should only cut 0 or 1 point. But here you can see it cuts it into 2 points. They met each other in 2 points, you see? So this is not a one-to-one case. So what does it mean? It means that for each y, for example, if I call it y1, I should have one unique point, not 2 points. So this is not a one-to-one case. But here, for the first drawing that we had here, for the first plot, you can see this one is one-to-one. Why is that? Because for each y, I have a single x corresponding to that. So, for example, I can check it from here. For this one, 1 corresponds to c. So this is one-to-one. But I should check for all of them, for all of the possibilities that I have here. These arrows shows us the way. For example, for this, we don't have any arrows. It means that we didn't use all the possible values that we had inside our codomain. Now, for 3, you see, only we have one value. This is okay. So this is an example of one-to-one case. If you, for example, have another arrow from A to 3, then it won't be one-to-one anymore. Again, I will show you in other examples. Okay, now determine whether the function fx x power 2 from the set of integer to set of integers again is one-to-one. In order to do that, let's take a look at this one. Sometimes the answer is yes, sometimes no. So the function fx is equal to x power 2 is not one-to-one. How can we prove that? By just finding one counterexample. If you just find one counterexample, it's just good enough to show that this statement is not true, that fx is one-to-one. And here they show it by the value 1 and minus 1. In this case, you can see we have two different y, for example, for 1 and minus 1. In both of the cases, if you consider x as 1 and minus 1, the final answer for it is 1. We shouldn't have such a case in one-to-one function. So each one of the x's should correspond to a unique y. So we show that 1 is not equal to minus 1, and we reach the same number. So it cannot happen in one-to-one. So if I show you here, this is the plot. So if I consider x equal to 1 and x equal to minus 1, so but we will reach the same answer for both of them, which is 1 inside my y-axis. You see, this is y, this is x. So for both of them, I reach the same answer. So what I mean by that, it means that if you draw a line parallel to x-axis, it will meet it in 2 points. So this is not one-to-one. One thing you should be careful about is that what is our domain? Because, for example, here, we show that this is not one-to-one function in the whole integer number. So what if I start from positive integers? You see, what if I don't consider the negative value of x? So domain is important. Domain is the set that you choose your x's from. So this is x power 2 if I only consider the positive integers. And if I'm talking about integers, it means that I'm only talking about these points, right? Otherwise, if I show it like the curly line like this, it means that we are talking about the real numbers. But assume that if we are talking about integers, we are just talking about these dots, these points. And of course, if you don't consider the negative points, you will find unique values for your images. Okay, so I think that you got the idea for one-to-one. Now, what about onto? The function f a to b is called onto if and only if for every element b belongs to b, there is an element a belongs to a with this one. The best way to show you guys about the surjective property is on this picture. So what do we mean by that? It means that if you consider all these possible arbitrary numbers, then you should use all of the codomain. In another word, your image should, the collection of your images, which is called range, should be equal to your codomain. That's the only way that we have onto function. So you see, all of the possible values here should be used. If you have another number, 0, then you don't have any arrow to it. It means that you didn't use this image. If you didn't use it, it means that, okay, this function is not actually onto. By just one counter example, again, you can prove it, this is not onto. Let me give you an example. Again, x power 2. If I consider R number that x's and y's, they can take numbers from real numbers, and in that scenario, this function x power 2 is not onto. Why is that? Because if I just draw a line parallel to x, I can find some points which are not inside the range. So if you can find such points that it doesn't cut the function in any points, then that would be a counterexample that this is not an onto function. But what if I define my domain, the range to be just from y more than or equals 0? So I can even limit my range as well. If you do that, then in that case, if you have this condition, then this function is onto. So these two examples showed you that it's very important how you define your domain and your range. Because if you limit them, in some cases your functions could be one-to-one, in some cases cannot be. The same story about onto. Now let's take a look at this example, which is very important in order to distinguish between all the things I just mentioned. Now, for the cases that they are one-to-one and they are, for example, onto, you already seen that. But this one, for example, is one-to-one but not onto. Let's see why. Can you tell me why? Yes, you see, we have an image which is not used, and that's why we can say this is not onto. Whenever you see such cases, right away you can say they are not onto. For example, you see, right away from here I understand this is not onto. But the rest of them, all of them are onto. Okay, but this one we have bigger problem actually. Even before checking whether this is onto or one-to-one, this one is not even a function. But why is that? Because from a single x, you reach two different y's. So the image should be always unique for each single x. That's why a circle is not a function. Why is that? Because when you just draw a line parallel to y-axis, you see, more than one, it will meet this function, or even this parabola like this. Again, this is not a function. So whenever this is not a function, we even don't consider whether this is onto or one-to-one or not. We don't care about them anymore. Okay, and why this one is not one-to-one? That could be a good question as well. And you see, for 2, we have two different x's. And that's why this is not one-to-one. Again, the same story we can say for this one. For 2, we have two different values for x. Okay, so this example is important in order to distinguish between a function and not a function, and also properties of a function. Now, in case that the function is both one-to-one and onto, we can find the inverse for that. So this is for sure. This is a if and only if case. It means that it implies, for example, when you have onto and one-to-one case, it implies that this function, you can find an inverse function for it. It means that now this is different from the image, we will reach the pre-image. Maybe it's better to show it again in the picture, you will understand about it better. But before going through that, assume that we have this arbitrary case that we consider A from the domain, and we will reach this image. And if you want to reach A from B, what we should do? We can define a function to do that for us. But not all functions can do that. Which functions can do that? Those who are one-to-one and onto at the same time. Otherwise, it's not possible. Now, take a look at this one. It means that if I want to reach A from B, then I should define inverse of the function. But before, we already showed you that how you reach B from A by using that function. So again, when this is possible, when we have the bijective property, which means that this is both onto and one-to-one function. Another important operations in functions is related to composition of functions. It means that you use one function inside another one, and we note that by this. What does it mean? It means that you consider the function name g inside the function f. What is this a? This is the arbitrary number that you use from the domain. Again, in examples, we can see it much better. But before the example, let's take a look at this picture. So it means that you have a set named A, you have another set B, and C also. If I want to calculate, for example, FOGA, it means that the composition of FOG, and insert this number as an arbitrary number. What is A? A actually belongs to the first set you see here. So A, you insert it inside this function. But how do we calculate that? First, you insert it inside G. As soon as you calculate it, then you use this one as the input of this function. So let's take a look at this example to understand it better. So let f and g be the functions from the set of integers to the set of integers defined by fx and gx like this. So what is the composition of f and g? And what's the composition of g and f? They are different. Let's take a look. Like, for example, FOGX. When I use x, it means that I didn't insert any arbitrary number. I just interested in the function, not to find the value of that. So when you write it like this, it means that gx should be inside it, like this. So what is gx? 3x plus 2. Just use this one as the input of f. So you just write this one. Instead of just a number, you can use another function inside. So whenever you see x inside your fx, then it means that you can use the input for that, whether this is a number or function, doesn't matter. Assume that I insert gx instead of this x. So whenever I see x, I just insert 3x plus 2. See? So 2 times 3, x plus 2 plus 3. And you can calculate it. And this example shows you that if you do it like GOF instead of FOG, not necessarily you reach the same answer. Okay, so these two are different. For example, for this one, I inserted fx inside this function. So whenever I see x, I insert 2x plus 3. So 3 times 2x plus 3 plus 2, and this one. So we already showed you about some graphs of the functions, but in order to define it officially, we can define them as pairs like this. So we already defined you what's the tuple because we use them a lot, and whenever we have only 2 elements, we call them pair. So by having this pair, we have A and B as a pair such that A belongs to A and FA is equal to B. So by using that, we can draw our function in the two-dimensional case. You already know how to do that anyway, but just to show you again. Assume that we are talking about just integers. We don't have lines between them. If we were talking about real numbers, we had. So this function, fx x power 2. If you have 0, then what is y? This is 0 power 2, which is 0. If you have 1, then you will have 1, 1. So for all of the numbers, you can have it and then show it on the graph. Now let's talk about floor and ceiling functions. We show them by these two notations. So whenever you use them, it means that you have maybe some decimal points in your numbers, but you are interested in integers, not decimal points. And sometimes you may want to decide to use floor function, sometimes ceiling. In case of ceiling, you are actually trying to run your number up. But in case of a floor, you try to just run down your number. This is the floor actually, this is the ceiling. If I say it by mistake before, let me correct it. This one is floor, this one is ceiling. Now, let's take a look at this picture. So this one is the floor. What does it mean? It means that if I have y only equal to x, don't consider this notation, just y equal to x, what should I have? The graph of that would be just a straight line going from these points and it goes to infinity, right? It should be a straight actually, not such a curl, but anyway. So in case when you apply such operation, it means that when I have, for example, 1.5 and I'm considering the floor of that, it means that don't consider the decimal point, but you should either go up or down. So if you are considering the ceiling or in this case floor, then you should go to the smallest integers that you can find. So 1.5 is between 1 and 2. So in case of talking about floor, you consider 1. In case of talking about ceiling, you will consider 2. So the closest integers, but in case of the floor, the smaller one. In case of the ceiling, the bigger one. So when you apply such a thing, it means that we shouldn't have decimal points now here. So it goes down instead of, for example, consider it above it, then it goes down. And you see in some of the circles, it is filled, some of them is not. It means that this point itself is included, this one is not included. So you see, whenever you are having integers, it's exactly the same as this line. But whenever you apply floor and ceiling, it can be changed either like this or this. You see, for the ceiling, it goes up instead of down when we talk about this line. So instead of having such straight lines, we have such cases. And in this case, actually, this should be the line. And this line goes up. But here, this line goes down. Anyway, it needs a little practice, but I think you got the idea about the difference between these two. And in this picture, it's nice also to show this point because here I also showed this one. So it's better to show this point, not to have this mistake, because this is our line. This is our line, and it should pass this point. There are some useful properties, and I've listed them for you here. It's not bad that you go through them. as you know, I don't ask you questions about proving these properties or something like that. So because usually we ask mathematicians about such questions. So I try to focus on the application of sets and functions for you. So you're now ready to read chapter 2, the first 3 sections. And please go through the examples in the book as much as you can. Of course, there are so many of them. Most probably you cannot cover all of them. But as soon as also you see the weekly assignment, you know what type of questions I may want to ask you, which you already seen for the first week. So guys, please, if you have any questions, let me know. Otherwise, I will see you on next Wednesday.